Okay, so good afternoon to all of you. So in the last class, essentially, what we discussed is we were discussing the examples of random variables, particularly the random variables whose range is closed, whose range is either a finite number or a countably infinite set. So we discussed that we have a experiment. We have a experiment. So we have experimental set, and we define a function from experimental set to real numbers. That is our random variable by definition. And random variable is what? Random variable associate with each outcome to a real number. Each outcome to a real number. So this is just formal definition of sigma field. We know that power set satisfies these properties. And then we discuss one result that if you have two functions which are real valued and defined on the sample space, then their addition is also a random variable. That means it is also defined on the I have shared the screen. Is it visible?
Yes, sir, it is visible.
Okay, so my screen is visible. Just in case you face any problem, you can rejoin again. Okay, so we have the sample space, which is a countable set. So whenever we have a probability space, then we have these properties. So whenever we have two random variables, then pointwise addition, pointwise subtraction, pointwise multiplication, and pointwise division, all of these functions are also random variables. So for example, quotient function we can define the way we define in the calculus or school mathematics. So that is also function from sample space to the set of real numbers. So that is also a random variable. X quotient y is also a random variable if x and y are random variables. So these are the examples using which we can construct more random variables. Given random variables, we can construct some more random variable by adding, subtracting, taking the division when the denominator is non-zero function, and we can do the composition. So we have a random variable, we can compose it with some real valued function to get another random variable, to get the another random variable. Similarly, if you have two random variable, we can compose with the multivariable function and create a new random variable. So after that, we discuss discrete random variables. What are the discrete random variables? Discrete random variables are those functions defined on the real valued function defined on the sample space whose range is finite or countably infinite set. Countably infinite set. So if the domain is finite set or a countably infinite set, then the range is countable or infinite, countable or finite set. So every random variable defined on the sample space, which is either a finite set or countably infinite set, its image is also so those random variables are always discrete. Those random variables are always discrete. Okay, so we have seen the example. Example is we have this is example of a countable set. We can associate the numbers, natural numbers, along with each outcome one by one. So that will give us an example of a discrete random variable. We can also use the indicator function. We can use the sign function. The sign function, even if the sample space is uncountable, sign function gives output 1, 0 or minus 1. So therefore it is a random variable which is discrete random variable. Discrete random variable. Okay. So then we discussed that if we have a discrete random variable, why we study discrete random variable. So if we have a discrete random variable, we can study its probability mass function. Probability mass function. So what is the probability mass function? We have an experiment. So in this experiment, which is a tossing of a coin 2 times, we want to find that what is the probability of getting one head, what is the probability of getting less than or equals to one head. So how to find such a probability? So to find such a probability, we need the notion of random variable, and we need the so what is random variable? Random variable is associating with the experiment some number. So how many heads? That is a number. So x associate hh to 2, ht has one head, so its value is 1. So in that way, this random variable associated with this experiment associate only 3 values, 2, 0 or 1. And then we know that there are 4 outcomes, so each outcome probability is 1 by 4. So getting one head is 1 by 4 plus 1 by 4. One head is 1 by 4 plus 1 by 4. So in this way we can find x inverse of 0, 1 and 2. 0, 1 and 2. So they are these values, this and this. And then once we know this, we denote this number, the probability of these events. These are the events. These are the events. Right? Collection of outcome is a event. They are the disjoint events. Disjoint events. So we can find probability of each of these event. That is our probability mass function. So probability mass function at 1 is the value of the random variable. Well, it is in the range of the random variable. So that is probability of the event. Probability of the event which is associated with one outcome. Probability of the event associated with the second outcome. The outcome 2, that is fx2. So what is the sum of fx1, fx2 and fx0? That is 1. So these are the properties of probability mass function. So we noted down these properties somewhere. Yeah. So what is probability mass function? Probability mass function is a function from real numbers to real numbers. It satisfies this property. It is defined in this way. Probability function is defined at the value in the range of fx as p of x equals to x. Probability of the event x equals random variable x equals to x. X equals to x. So if x is not in the range, value of the fx is 0. Value of the fx is 0. So that means it is enough to find the value of the random variable at the points in the range of the random variable. Points in the range of the random variable. So these are the properties which we discussed in the last class, that we have the probability space and we have a discrete random variable x. Then our probability mass function fx, which we simply write by f, because now we will keep x in our mind that we are considering f associated with this x. So every time we will not write fx, we just write simply f corresponding to this given discrete random variable x. So this f probability mass function associated with this random variable is non-negative. It is greater than 0. This set is finite or countable because we are taking discrete random variable. So the range of x is countable or finite set. And when we add all the values of fx, it will be 1. It will be 1. So now you can see that these are actually the properties of the probability function. That probability function of any element in the sample space is non-negative, right? P of x is always non-negative whenever x is in the sample space, and the addition of px is 1. Addition of px is 1. So that means this probability from this probability mass function is associated with the probability function. So that we'll see now. So in this proposition, what is given? It is given that discrete random variable is given and probability space is given. We get the probability mass function. Probability mass function which satisfies these three conditions. These three conditions. Now the question is reverse. Question is reverse. That means if we are given, so we've seen this example. So this example also we have seen, and then this exercise was given. So did you try this exercise? Okay, so let me quickly do some of these computation and then we'll move further. So in this exercise, what was given? We were given 3 points, W1, W2, W3. So like in tossing of a coin, we have two outcomes, head or tail. So instead of that, we are getting three outcomes here. And then we are defining probability function on these three outcomes. These three outcomes. So since there are three outcomes, it is natural that each outcome has same probability. If we assign uniform probability function, then we have assigned P of W1 is 1 by 3, probability of getting W2 outcome is 1 by 3, and that way. And we define three random variables. So X is defined in this way. So each element in the domain, the value is given of X. Similarly, Y random variable is defined, which is a function from omega to R. This is 2. And similarly, random variable Z is given. So we can see that random variable X is not equals to random variable Y. So can you so is it clear why X random variable is not equals to random variable Y?
Because sir, it's clear that x, y, and z are different events, so random variable are not same.
X, Y, and Z are
Different,
actually
sir,
giving
because for omega 1 it's 1 and for sim omega 1 y is 2.
Y is 2. So basically what we are seeing, we are looking at this function. So what are the random? So what you are saying is correct. So basically what you are saying is that this X, Y, and Z are essentially functions. So random variables are essentially, they are the functions. And we say that the random variables are not same. That means basically they are, as a function, they are not equal. So as a function, they are not equal. So as a function, they are not equal. That means we know that two functions are not equal, means they are not equal at a particular point, right? So therefore, what you said is correct, that X is not equal to Y because X of W1 is 1 and X of W2 is 2. So as a function, they are not same. They are not same. But on the other hand, we need to show that their probability mass functions are same. Their probability mass functions are same. So to show that, so probability mass function is also function from real number to real number. So that means to prove that the probability mass functions are same function. So I'm not solving it fully, but you can easily do that later. So what we need to show that, we need to show that fx is also function from R to R, fy is also function from R to R, and fz is also function from R to R. R to R. And we know that if we need to find the probability mass function or only at the range of the random variable. So what is the range of x? Range of x is 1, 2, 3. Range of y is 1, 2, 3, and range of z is 1, 2, 3. So fx, fy, and fz are 0 other than the points 1, 2, and 3. So that we already know. So only thing we need to check is fx, fy, and fz. Only we need to show that fx is equals to fy is equals to fz on the set 1, 2, and 3, because 1, 2, and 3 is the set which is the range of x, y, and z. So let us first check whether fx of 1 is equals to fy of 1, because we know that x of 1 is not equals to x and y are not same function, but whether fx1 and fy1 are same. So what is fx1? By definition, it is probability of the function x equals to 1, and fy1 is probability of x equals to 2. X equals to 2. So what is this x equals to 1? Means all those points in the domain of x for which xw is 1. Xw is 1. So let us go to the values of x. So when x becomes 1, only possibility is w1, because at w2 it is 2, at w3 it is 3. So x is 1 only at w1. So this is probability of getting w1 of the event w1. And we know that probability of w1, w2, w3, probability of w1 is 1, w1 is 1. Sorry, 1 by 3. Probability of wi is 1 by 3. So probability of w1 is 1 by 3, w2 is 1 by 3, w3 is 1 by 3. So similarly here, what will be probability of, here the variable is y. So I did mistake. The variable we are taking is y. So when y becomes 2, so in the definition we have taken y becomes 2 on the w1 itself. W1 itself. Sorry, again I did mistake. It should be 1, right? So when y becomes 1, it becomes 1 on w3. Y becomes 1 on w3. So this is probability of w3, which is 1 by 3. So even though x and y are not same function, they coincide at value 1. Similarly, fz also we can find, that is z equals to 1. Z becomes 1 at w2. So that is probability of w2, which is also 1 by 3. Which is also 1 by 3. So we can see that fx1 equals to fy1 equals to fz1. Similarly, we can check. Similarly, we can check that fy1 equals to fy2 equals to fx2 is equals to fz2, and similarly for the third point. Right. So therefore, fx, fy, fz are same at every point. So they are same function. So the random variables are not same in this example. Random variables are not same, but their range is same. Range of x is same as range of y is equals to range of that. Yes. Right. But on the other hand, we have the range is same, but the functions are different. their probability mass functions are same. Probability mass functions are same. Okay. So now using this, we want to study the reverse of this statement. The reverse of this statement. So what is the reverse of this statement? The reverse of this statement is that here we started with the discrete random variable and the probability mass function. We got the we started with the probability space along with the random variable. We got the probability mass function. Now suppose we start with the probability mass function which satisfies these three properties. That means fx is non-negative, fx greater than 0 is a finite set or a countable set, and the third condition that it adds up to 1. It adds up to 1. Then using this property, can we construct a random variable and a sample space? Random variable and a sample space corresponding to the given probability mass function. Given probability mass function. So for example, in this example, what is the probability mass function? Probability mass function is fx at 1, 2, 3 it is given. So at 1 its value is 1 by 3. At 2 the value is 1 by 3. At 3 also its value is 1 by 3. Right? Its value is 1 by 3. So cumulative value is 1. If we add all these three numbers, cumulative value adds up as 1. 1 by 3 plus 1 by 3 plus 1 by 3 is 1. Is 1. So now the reverse question. If we are given any three numbers which adds up, which are non-negative numbers, can we associate an experiment and a random variable corresponding to that? So that is the next statement. That is, suppose that so let f be a function from R to R which satisfies the properties so first property is that it is a non-negative function. So we know that probability of any sample point is non-negative. So this property is corresponding to that. The second property is we need to have a countable set or a finite set. So the points at which fx is non-zero, fx is strictly greater than 0 is a finite or a countably infinite subset of R. So this condition is related to the random variable is finite or countable range. So discrete random variable condition. And third condition is the total probability is 1. So that means it adds up to 1. It adds up to 1. So on this set, basically on the set S. So if any such function is given, real valued function is given which satisfies this property. So can we find corresponding sample space and the whose probability mass function is this function? Probability mass function is this function. So then there exists probability space omega f and p and discrete random variable x on it such that f is the probability mass function of x. of x. So for example, 1 by 2 and 1 by 2 is given. That is a function f from R2 are such that f is half at some point and f is half at other point. Only this point it is not zero. Then the corresponding experiment is tossing of a coin. So getting head is probability half, getting tail is probability half. So similarly, if trivially we associate here the experiment, what is the essentially the sample space. So since we have this set which is finite or a countable, so we know that if we have a finite or a countable set, any function, any random variable we define on a set is also finite and countable set. It has image which is finite or countable. So simply take omega to be the set S, omega to be the set S, because it is a countable or infinite set. So since S is at most countable, so by we say it is at most countable means essentially it is not uncountable. It is either finite or countable set. So therefore we can take the sigma field to be the power set of X. Is the power set of omega, which is S. Omega is S here. So what is S? S is the points where the function is non-zero. Function is strictly greater than 0. Strictly greater than 0. And so what is the trivial function we can define here? So we have a set now, which is essentially what is this set? This set contains all the real numbers. What are the element of S? They are the real numbers. And we need to define the random variable X from S to R. So this is a subset of real number, and this is the set of all real numbers. So the trivial way to define the random variable is like an identity function. So basically it is called the inclusion function. What is the function? Function is trivial. You define all the elements the same element. All the elements the same element. Right? So usually we write x w, but here since we are taking the same element, w is x. So we are denoting here x itself because input output is same. And now we define f, we define the sample space. Only thing we need to define the probability function. So since omega is a finite or a countable set define, so it is enough to define the probability function. It is Okay, I got disconnected. Okay, am I audible now?
Yes,
Yes,
sir.
So what was the point where we got disconnected?
sir. Not much. There only, sir. Last point.
Okay, last point. So yeah, so this we define this probability function to be the probability map to be fx itself. So what is f? F is the given function. F is the given function which satisfies this three property. Using that, we define px. So px is fx itself. Px is fx itself, and our random variable is this. Random variable is this. So now, using random variable, which we define using the function f, we need to check that corresponding probability mass function is f itself. So note that fx of x. So what is fx? Fx is the probability mass function corresponding to random variable x. So that is probability of x equals to x. Probability of x equals to x, and x is the identity function. So that means that is exactly probability of x, and probability of x is coming from the given function fx. Right. So this probability mass function, this is what? This PMF. So PMF coming from random variable x is same as the given function fx at every point. At every point. Right. And on the other points, it is anyway 0, because we need to bother about only points of the set S. Points of the set S. So therefore, we will be either discussing the function which satisfies this property, then the corresponding random variable we have is the identity function, and otherwise we have the experiment. Using that, we will find the random variable. Okay, so what we are going to discuss today? So today we will be discussing certain special discrete random variables. So far we discussed discrete random variables and the corresponding probability mass function. Now we will discuss discrete random variables which are related to the Bernoulli random variable, uniform probability, and the binomial experiment, binomial probability model. So these three we are going to discuss now as a special case of discrete random variable. So first one is so what is this topic? That is standard. So there are many discrete random variables. We are discussing standard discrete models. Basically related to the standard uh, experiments. So we know that the experiment we are considering is basically the tossing of coin, roll of a die, this experiment. And the second thing which is required for probability mass function is the probability function. So we know that there are different ways to define the probability function. So these two things we'll be using in this topic. So the first thing is discrete uniform random variable. Discrete uniform random variable. So we know that if we toss a coin, there is a uniform probability function we can define. So there are two outcomes. That means probability of each outcome is half. If we roll a die, then the probability function is the uniform probability function. If we define, then there are 6 outcomes. So each outcome, the probability is 1 by 6. Probability is 1 by 6. So basically here we are discussing the probability sample space, which is a finite sample space, right? So So suppose that we have a experiment in which uh, our random variable takes finitely many values. So suppose that we have an experiment in which the random variable takes finitely many outcomes, takes finitely many outcomes, finitely many outcomes. Say it is taking values finitely many, that means it is 1, 2 up to n, 1, 2 up to n. So then the probability mass function for this variable, random variable, then the PMF for this random variable x. So let us say this random variable is x. So this will be fx at I. So ith outcome, right? I belongs to 1 to up to n. So that is exactly the probability of the random variable is equals to I. This will be 1 by n. This will be 1 by n for every I is equals to 1 to up to capital N. 1 to up to capital N. So what does this means? So this means, for example, we have an experiment like tossing of a coin, tossing of a coin 2 times, and then we have the outcome which is 0, 1 and 2, right? If we toss 2 times, so outcome is head, that is uh, either 0 head, 1 head or 2 head. So that, suppose the probability of getting 0 head we assign 1 by 3, 1 head is assigned 1 by 3 and 3 head we assign 1 by 3. Why we assign? Because we are considering the uniform probability here, uniform probability. So if we have an experiment in which the outcome uh, gives a gives a random variable and which follows the equal probability rule, that means it satisfies this property, and such a random variable is called the discrete uniform random variable. So such a random variable x is called discrete random variable with parameter capital N. So we denote parameter capital N, that means this random variable has essentially n distinct values in the range, n distinct values in the range. So it is a discrete random variable. It is okay. I did not mention it is a discrete uniform. Uniform. So what is uniform means? Uniform means the probability of x equals to I is 1 by n. That is equal for each outcome, right? Equal for each n outcomes. Each n outcomes. So the second model is the Bernoulli model. Bernoulli random variable. So can you recall what is the Bernoulli probability function? So if you have the experiment head and tail tossing of a coin, probability function defined by Bernoulli, on that So we need to define the probability of head and tail, but we will not take the uniform probability. So that means we will not take half. So in general, we will not take half. So that is the Bernoulli.
Sir, P and 1 minus P?
Yes, so that is a P and 1 minus P. So it is kind of a ratio, In ratio test, we take R is between 0 and 1. So similarly here also we take the value of getting success. Let us say head is a success. Then getting success is P, and the complement, that is tail, that is 1 minus the success probability, that is 1 minus P. That is 1 minus P. So consider the toss of a coin, uh, which comes up as a head, which is getting head has probability P, where P is between 0 and 1. P is some number between 0 and 1. Then, so that is basically what we are saying is, that is probability of getting head is P. So therefore probability of getting tail is basically the complement of head. So that is 1 minus probability of H, which is 1 minus P. So you already know this. It was discussed in earlier part of the course. So this is Bernoulli model. This is given by Bernoulli. And when we take P is equals to half, that means when the probability of getting head is half, probability of getting tail is also half. So in that way, this model generalized the previous model, which was the uniform one, right? Uniform random variable. So what will be the So this is getting head and tail. So similarly, you define the random variable. So define the random variable. X from this experimental space X to R. What is experimental space here? That is, we know that it is head and tail. So H to R defined by, let us say, binary digit. So that is 0 and 1. So this is success. So let us denote by 1. Failure is 0. So what does the probability mass function, the Bernoulli random variable, what is the PMF of Bernoulli random variable? So Bernoulli random variable is this. So to find PMF, we need to find fx, right? So there are only two values it is taking. So basically fx of 1 and fx of 0. Fx of 1 is probability of x equals to 1, is probability of x equals to 0. This is basically probability of h, this probability of tail, and this is we know that this is p, this is 1 minus p, this is 1 minus p, right? So this is essentially the probability mass function of this Bernoulli trial. And as I mentioned, when we take p is half, and in the previous experiment, when we take n equals to 2, we get this is half, right? N equals to 2. If we take, this will be half. So essentially we have half plus half is 1. That is the special case of this trial. So when we take the trial here of so here if we take a dice, then we know that probability will be 1 by 6. If we roll a die, then the probability of every outcome of random variable will be 1 by 6. So same way here, so here we define only head and tail. So p and 1 minus p. Suppose we roll a die. So that means we will have 6 numbers, right? So in that case, what will be this condition? So in Bernoulli model, we have two outcomes, head and tail. So basically we are getting P and Q, where P plus Q is 1. P plus Q is 1, right? Where P and Q are non-negative, and basically Q is P minus 1. Q is P minus 1. So we are breaking 1 into two parts, P and Q, so that P plus Q is 1, P and Q are non-negative, and Q is essentially 1 minus P. So if we have 6 outcomes when we roll a die, so that means we have P1 instead of P and Q, we have probability of each of that. That means P1, P2, P3, P4, P5, P6. Each of these is non-negative because that is probability, and their sum is 1. Total sum is 1. Right. So that way we can extend this Bernoulli trial for we can define the random variable. So instead of 0 and 1, in that case we can define 0, 1 up to 5. So modulo 6 kind of thing. Anyway, that is just kind of extending this Bernoulli's idea for the dice. Okay, so this experiment we have considered head and tail, but it can also be related to this experiment. So this experiment is getting head and tail as outcome, but it can also be related to other experiments, like whether there will be rain today or let us say tomorrow or not, right? So head means there will be rain, tail means that will not be rain, right? So similarly the other experiment is either a telephone number of some person will be free when we call or not, right? So telephone number or mobile number, whatever we call. So these are the experiments which are related to the experiment of head and tail. So whatever information we are discussing has application to the other experiments also. So third type of probability function is binomial probability function, where we are getting the terms like binomial expansion, binomial expansion. So consider an experiment that consists of n independent tosses of a coin. So here the experiment is consists of n independent tosses of a coin. So independent means they are not dependent, right, on each other, in which, in this experiment, in which the probability of getting head is head in each trial is is p, right? So every time getting head, the probability is p, where p is between 0 and 1. So we are getting the idea of Bernoulli, but we are doing it, the experiment, essentially n times. We are tossing the coin n times. Each time, at each time we toss the coin, getting head, the probability is p. So in this context, what is meaning of the of, so here independent tosses means, so when we toss the first time and the second times, so they are the events, so they are independent events. So this means the events a1, a2, an are independent, where what are the, so ai is the ith toss is head. So this is the event. So what is a1? The first toss is head. A2 is second toss is head, in that way. Each toss getting head is independent. It doesn't depend on the previous event. So first toss, it is head or not. The second toss does not depend on the first toss, in that way. So for example, so this means what? This means the probability of this event. So this is basically a1, a2, a3. So we are tossing 3 times, right? Tossing 3 times. So 3 outcomes we are getting. So this is independent. Independent means this probability is basically probability of h, probability of t. Right. So independent means these two are equal. So this is independence. So in this experiment, we say it is independent. That means whenever we have 3 outcomes HHT, its probability of this combined event is multiplication of probability of first outcome, second outcome, and third outcome. And then we know that probability of H is P. That means probability of T is 1 minus P, right? Using the Bernoulli model. So therefore, what will be this probability of HHT? Probability of HHT is P into, so that is P square into 1 minus P. Probability is 1 minus P. So in general, suppose we have, so in general, this we can do for n times tosses and getting k heads. In general, in the event of tossing coin n times, so we are tossing the coin n times with this independence rule and getting k heads and getting k heads. So in this event, in which we are getting k heads. So here, if we find the probability of HTH, then what will be this? I should write capital P here. So what will be the probability of HTH using the independence rule?
So same as HST.
Same, because it is an independent event. So again, it is PH, PT, PH, and that is P into 1 minus P into P. That means again it is P square into 1 minus P. Correct. So this is same. So that means how many H are coming, that is only important, right? So therefore we are saying that if we have any event of tossing coin n times in which we have k heads, so then the probability of this event will be same. The probability of this event, here we are getting k heads, so that means p power k, and we'll get the other tail, so that means probability of tail power n minus k, n minus k. You can see that these terms are like binomial coefficients. They are like binomial coefficients where the number of heads can be either 0, 1 or up to n. Right? Number of heads in the experiment of tossing n times will be either 0, 1 or up to n. Up to n. Right? So now we have this experiment, tossing of coin n times, getting head or tail. So now we can define the corresponding random variable, which we usually take is a getting n number of getting heads, number of heads. All right. So again, in this experiment of tossing the coin n times, tossing the coin n times, we define the random variable x from omega to r by, so omega is clear, basically that is n string of h and t. All the elements omega is n strings of h and t, and it is defined by essentially x omega is the number of heads, the number of heads in 10 independent tosses. So in this experiment, we have defined what is the random variable. So what are the values of this random variable? So values of this random variables is so therefore what is the range of x? So range of x is either we get 0 head, 1 head, up to n head. So right, so possible heads, possible number of heads. So range, so why we define, we found range because we want to define the probability mass function. So therefore probability mass function, which is binomial probability mass function of this x is, so basically it is fx of, we need to define at each k, where k is running from 0 to n, k is running from 0 to n. So these are the range elements. What will be these? This will be basically probability of x equals to k. X equals to k. That means all the outcomes of the experiment, all the points in the sample space in which we have k hits, Now the ways to choose k elements from n toss sequences, right? So that is basically this is probability of exactly k hits come up in n toss sequence. So basically we are choosing k from n. So that means we have nck choices, nck choices of k hits, and the probability is basically p power k 1 minus p n minus k. So what we counted here, we counted here the probability of one of these, right? One of this event. And how many such events is there in which there will be 2 hits out of 3? That will be 3C2. Right? So similarly here we have nck in general, and probability of one such event is this, and there are nck such events. Okay, so only thing we can here verify that we know that if we have a probability mass function, it adds up to 1. So note that we have summation k0 to n fx of k. So it is anyway 1, but let us verify this for this variable. So that will be essentially k0 to n nck p power k 1 minus p nck n minus k. So this is exactly the binomial expansion of p plus 1 minus p power n, right? And we know that p plus 1 minus p is 1, so this is 1 power n is 1. Right? So in this subsection we discuss the binomial experiment, which is related to the binomial probability function, where we are tossing tossing a coin n times, which is a fair coin, but probability of getting head is p in this experiment, and we are tossing it n times, which is an independent event. At each stage it is independent, and then we get the probability mass function is this nck p power k 1 minus p power k n minus k. So again, this binomial expansion is a kind of generalization of the Bernoulli expansion, because here the same thing we are doing 10 times, right? So in that way it is a kind of general thing. So now the last probability discrete random variable which we want to discuss is geometric distribution. So in the geometric distribution we have so far we discussed the discrete random variables, which are essentially finite outcomes, but we also need to take an example in which we have a discrete random variable which has not necessarily finite but the countably infinite outcome. So experiment, we know that tossing a coin until we get head, tossing a coin until we get the first head basically. So let us consider that experiment. So let us consider a random experiment and in which we toss a coin until we get we get the first head. So we know the omega is basically h, th, tth, etc. So this experiment we are considering, and in this experiment, if you say that at each toss getting the probability head is p, right? So here also we are taking the same idea of the previous binomial case. So the events are independent, right? So we assume that each coin toss is independent. Right. So basically what we are emphasizing here is essentially whenever we have trade of head and tail, its probability will be considered in this way. Right. So probability of will break down in this way. Okay, so again we are going to use the same idea, 0 less than p less than 1, where p is the probability of the head. So suppose the probability of h is p, probability of getting head is p, where 0 less than p less than 1. So therefore probability of tail is 1 minus p. Right. So therefore in this experiment we have, if you remember, we have assigned a random variable to this event as so x from, in the last lecture we defined that x of h is 1, x of th is 2, right, and so on. This is the random variable because it assigns each experimental outcome to the real numbers. So this is a random variable. We want to find its probability mass function. So note that the probability of t t t t h. So how many are these? This is k minus 1 times. So suppose we have k minus 1 times tail, and then we have h. What is the probability? Probability is 1 minus p power k minus 1. Probability of tail is 1 minus p. So it is this one, right? It's true for all k is equals to 1 to up to so on. 1 to up to so on. So what is this number? So this number is number of tail plus 1. Number of tails plus 1. So here there is no tail, 0 tail, plus 1 is 1, 1 tail plus 1, 2 tail plus 1. Right. So in that way, 3 is 2 tail plus 1. 2 tails plus 1. Okay. So what is 2? 2 is assigned to the event which has 1 tail. In that tail, in that case, what will be probability of x equals to k? So this is basically probability of getting. So this is k, right? This k means it is the value of the random variable is k. So random variable is k. This is k. K is 3 means 2 tail plus 1, right? So that is getting k minus 1 tails. K minus 1 tails, right? The probability of getting k minus 1 tails, that is this one, so that we know that it is p 1 minus p power k minus 1. This is true for all k 1 2 up to so on. So we found probability mass function in this case whenever we have this experiment of tossing a coin until we get head. And here also we know that this series is convergent because what is the reason?
So P is less than 1.
P is less than 1, therefore 1 minus P is less than 1, right? So if you call 1 minus P is Q, then this is geometric series in Q, and Q is between 0 and 1, so it is convergent. So you are right. So this is okay. Let me expand. So I think you already know this, but yeah. So this is P plus P 1 minus P, that is P times 1 plus 1 minus P plus 1 minus P square. Yeah, so this was discussed earlier. So A upon 1 minus 1 minus P. So that is 1, P by P is 1. Here geometric series we are using, this equals to this because 0 less than 1 minus P less than 1. So geometric series. Okay, so this is also probability mass function corresponding to the geometric distribution, and that's why we call it geometric distribution, because it is related to the geometric series. So now we have one proposition out of this. So what this says? This has some relation with the memoryless property. So what this property says that if you have a geometric random variable, let x be a geometric random variable with the probability of success is p, where 0 less than 1, p less than 1. So probability of success means getting head is a success, right? So in that way. So so what I have written, let x be a geometric random variable with the probability of success is this. So in this experiment the probability of success is p. So then for every natural number, so then for each non-negative integers, so each non-negative integers m and n, we get, so m and n are non-negative integers, means they are either 0 or natural number. So we get probability of x greater than n plus m with probability x greater than m. So this is a conditional probability that equals to the probability of x greater than n. So remember that we are discussing the independent events, and then we know that what is the rule of the probability of the conditional probability. So here you can see why it is called memoryless. Why it is called memoryless means you start with m or you start with 0. So this you can write as x greater than n with x greater than 0. So then these two probability are same. So from which m you are starting, it doesn't matter. In that sense, this has some applications. Therefore, it is called the memoryless property. Memoryless property. So we know that p probability x greater than 0 is total probability, because all points in the sample space will be there. So that is 1. So it is not written here. So proof is quite trivial, that probability of x greater than n, that means basically the value of x is starting from n plus 1. Starting from n plus 1. So k is equals to n plus 1 to infinity. Probability of x equals to k. Right? So value of x is either n plus 1, n plus 2, or infinity. And then we know that probability of x equals to k is p into probability of x equals to k is p into 1 minus p power k minus 1. K minus 1. P into 1 minus p power k minus 1. K is from n plus 1 to infinity. Again, geometric, this is also geometric series, kind of tail of the series. So this we can write as, we can take common term, and the remaining series is 1 plus 1 minus p, 1 minus p square, and so on. Right? And that will be essentially this is again geometric series. Its sum is 1 by p. We already noted that the sum of this series is 1 by p. So therefore, this is p into 1 minus p power n times, this will become 1 by p. So pp will cancel, it will be 1 minus p power n. So the right hand side we have computed. The right hand side we have computed. Okay, so left hand side I am giving as an exercise. You do that, otherwise we will discuss in the next class. We will discuss in the next class. Okay, so let me stop here. If you have any doubt, you can ask now.